Okay, so today's lesson is on angles of elevation and depression, and it's being done while lasagna is being made in my kitchen, so there may be some interruptions. We'll see how we go. The cook's been told to be quiet, but she's a little bit of a pain. Angles of elevation and depression, we're just concerned with either looking up at something or looking down at something. So when we're looking up at something, that's an angle of elevation, which is here, and in this case, that's the perspective of the car here, that angle there. Looking up at the helicopter, that angle up is an angle of elevation. In contrast, an angle of depression is if we're already up high and we're looking down at something, and so that's this angle in here, so the helicopter's view of the car. Importantly, the angle of depression is not this angle in here. If we imagine this forming a triangle, the angle of depression is not that angle there. It's going to be effectively outside our triangle. So what may be fairly obvious with this is that we kind of end up with a situation of the angle of elevation always equaling the angle of depression, which kind of makes sense. The angle from the horizontal down from an object up high should be the same as the angle from that object we're looking at up to the original object. I'll explain what I mean by that in a second. So if we go through here with the example provided, what is the angle of elevation of the helicopter from the car? So we're really important, the words of and from. This matters in bearings as well. We're trying to think about where we are and what we're looking at. So we're wondering what the angle of elevation of the helicopter from the car is. So we're talking about this angle down here, and that is that funny B, which is a beta symbol. And the angle of depression from of the car from the helicopter. So we're in the helicopter, we're looking at the car, and that's going to be alpha. All right. And it says explain why alpha equals beta. Well, quite simply, the horizontal is always going to be parallel to any other horizontal, just like a north line is always parallel to a north line. So if I've got two parallel lines, and if we think about this, I'll run a bit of it's probably a bit thick. We'll go with a thinner highlighter there. You might be able to see here what we're probably going to get is one of those Z angles. We've got the angle on either side, and so that's because the reason why they're the same is because they're alternate angles. So alternate angles on parallel lines. So this basically always generally creates a right angle triangle. We're usually concerned about a upright object like a tower or a cliff or something like that. And if we know the distance, either the height of it or distance to it, we can work out other things around it. We basically create ourselves a little right angle. So this example here is perfect. We've got a tower. We're just going to assume, unless the Leaning Tower of Pisa is used as an example, we're going to assume that when people build towers, they build them upright. So Joe stands 40 metres away from the base of a 25-metre tower. And what's the angle of elevation from Joe to the top of the tower? So we're trying to find this angle in here. So all we're left with is a trigonometry question where if we're thinking about this angle, we've got an opposite side and we've got an adjacent side, the side next door. So if I was thinking about opposite and adjacent, I'd probably think about the tan ratio. And that just simply says that tan theta equals the opposite over the adjacent. Now in this case, we don't actually know the angle, but we do know what the opposite and the adjacent are. The opposite is 25 and the adjacent is 40. So therefore, if we want to know that angle, we're going to have to use that tan to the minus 1 button, 25 over 40. So we plug that into our calculator and we get, so shift tan, because we're finding an angle, 25 over 40, close our brackets, and that'll give us an angle. And in this case, it's 32 degrees. I think it's a nice to the nearest degree. Okay, moving along to our next example. we've got the angle of depression from a ship, of a ship from the top of a 220 metre vertical cliff is 32 degrees. Find the distance of the ship from the base of the cliff, correct to 1 decimal place. So we've got a nice vertical cliff here. We know what the angle of depression is. Now, as we said before, this angle here is going to equal that angle there. They're going to be the same. So this here must be 32 degrees because those two are parallel. Remember that the horizontal lines are parallel when we're talking about an angle of elevation or an angle of depression. So if I know that, then I'm interested in this side here. That's the adjacent side. And I know this side over here, that's the opposite side. So when I've got an opposite side I'm interested in and an adjacent side I'm interested in, that must be the tan ratio, SOHCAHTOA, TOA. So tan of any angle is the opposite over the adjacent. So in this case we know the angle, and that's 32 degrees. The opposite side is 220 metres, and the adjacent's the bit we don't know, and that's given in the diagram by D. So this is one of those situations where if you want to use your algebra, that's good, but you can just use the little trick and know that those two are going to swap around. So you're going to end up with D equals 220 over tan 32 degrees. So if I put that into my calculator, so 220 over 10. Now we're not using the shift here because we're after a distance. And close those brackets, and there we go. So we're left with 352 to 1 decimal place. That's going to be 352.1 metres. I did 1 decimal place because that's what it asked for in the question. Make sure you read that there. Okay. So you can see these questions aren't really that much different than other trigonometry questions. We just have to understand the nature of the problem-solving question that's given to us. This next one's a little bit more interesting. Well, not interesting, difficult, I suppose. So Alex is standing on the roof of his apartment blocks. So there's Alex up here. I'll just put a big A there so we can see that's where Alex is. And he can look up to a bird on another building, or he can look down to a dog standing at the street at the base of the same building, and the two buildings are 280 metres apart. So the first question is, how far is the bird from Alex? So in this particular case, what we want to know is this distance here. I'm going to call that X. So we want to know how far away is he from that. So if we think about this, with reference to this 14-degree angle, I've got this distance here, which is the adjacent side, and I've got this distance here, which is the hypotenuse. So if I'm interested in the adjacent and the hypotenuse, I think of SOHCAHTOA, that's going to be cosine. So cos of any angle is just equal to the adjacent over the hypotenuse. I fill in what I know. What do I know? Well, I know the angle, that's 14 degrees. And the adjacent side is 280 metres because it'll be the same up here as it is down below. We're going to assume that the people who build buildings build them straight. So 280 metres over, and the distance we want to know is that distance to the bird, and we've decided to call that X. So once again, just like the previous time, we can switch around those two things, or you can do your algebra to work that out. So X over 280 times cos 14 degrees, sometimes divided by cos 14 degrees. So if we run that through our calculator, we're going to end up with 280 over cos 14 degrees, close our brackets, and that's going to give us 288. Did it say how far? We'll go to 2 decimal places, 288.57. And that's in metres, and we might just say that's the 2 decimal places. Okay, and then the next question is, how far is the bird from the dog? So in order to know that, we're going to have to actually know two things. We're going to have to know this distance here. Actually, I might do this in a different colour. We're going to have to know this distance here, which I'm going to call Y. And we're going to have to know this distance here, which I'll do in a different colour again. We'll do that in blue. We're going to have to know this distance here, which I'm going to call Z. Actually, I won't call Z, I'll call it W because that's easier for me to write. So I'm going to need to know those two distances. Now, as far as that first one goes, there's two ways I can work that out. I could use trigonometry again, or I could use Pythagoras, because I now know in this right angle triangle up the top here, I'll just colouring him in blue. In that right angle triangle, I now know two sides, so given it's a right angle triangle, I can use Pythagoras to find the third, or I could use trig again. It doesn't make a difference, whichever way I prefer. So in this case, I might use Pythagoras. So how far is the bird from the dog? So to find y, and I'll do that in purple, we're just going to use a squared equals c squared minus b squared, which in this case, we know that c squared, we just worked that out, so that's going to be 288.57 minus, and that other length that we know is the base, so that's going to be 280 metres squared. And if I plug that into my calculator, obviously in this case, I called that y, so I'll change that to y squared so it makes sense. So we're going to go 288.57 squared minus 280 squared, and that's going to give me 4872.6449. Oh, sorry, 4872. Obviously, I need to take the square root of that to find out what y is. So if I just press the square root of and use the answer key, and that'll give me 69, we'll call that 69.8 metres. So that's how far the bird is from the dog. Now we've got to work out the other piece of information we need. We need to work out what W is. And in this case, we already know that this distance here is 280 metres. So in this particular triangle, we're interested in, we've got an opposite side and we've got an adjacent side. So we're going to be looking at tan for the opposite and the adjacent. So I'll do that in the same colour as I made W. So tan theta equals the opposite over the adjacent. In this particular case, that means tan of, how much was that angle? 33 degrees. Equals the opposite side. The opposite side is the bit we don't know, that's W, over the adjacent side, which is 280. So we're going to end up with W equals 280 tan 33 degrees. And if I plug that into my calculator, that's going to give me 181.83. And that's metres. So now the total distance is just going to be those two added together. It's just going to equal that y plus the w, which is 69.8 plus 181.83. And plug that into our calculator. So I'll just take that number and add the 69.8 to it. And I end up with 251.6. Now you may well end up with a slightly different answer if you use trigonometry first, and that would be to do with rounding error and those sorts of things. Finally, I think this is the final example. Yes, it is. We've got Maddie on the White Cliffs of Dover. So I'm just going to talk about how you'd go about this one first, and I probably won't solve it. So in order to find the distance, in order to find this one, I'm going to have to find out this total distance here using this triangle here. So if I use that triangle there, I'll be able to find the total distance. Then I'm going to have to take away from that the distance to the cliff from the new position, because what we're after is we're after this distance here. That's the distance we're being asked for. So how far did we move? So I'm actually going to need the blue distance. If I call that y, I might do that in the same color pen. And if I call the black distance x, what I'm actually going to need in the end is the distance is going to be x minus y. And I've run myself out of time, but that would be how you'd go about that one I'll put a full solution on OneNote for you. Thanks.